Okay, so welcome back to the CAMI hardware verification lecture track. Yesterday I introduced the basic domain of digital hardware development, and we worked through a series of examples of building a pretty primitive but functional adder for large bit vectors. And one thing I didn't emphasize so much there is we actually proved the correctness of an infinite family of adders. It was one theorem that applied to any number of digits that we might be using to represent our numbers. But we still only had so-called combinational circuits. They were basically just functional programs that evaluate to compute some output given the input, and everything runs instantly. Today I want to focus on stateful components in hardware and how we should specify those and verify them in a nice modular way where we can take a big system, break it into parts, verify the individual parts, and then with very little effort combine those theorems together. And to introduce how we model this in CAMI, I'm going to start with some classic material in what's called process calculus and how we think about interacting concurrent processes, because different components of a hardware system are interacting concurrent processes in a sense where they talk to each other with wires that connect them. So let me start out with a simple language here. I think I might want to fiddle with these lights. It's a little scary, but that's probably a little better. Is this better for writing on the board? Or is this okay? So I'm going to define the grammar of a language of processes. Think of these as concurrent programs that will communicate with each other using message passing. And the easiest kind of process is a done process that's just going to sit there forever doing nothing. And I said these are message passing processes, and they communicate with each other through channels. So I'm using an exclamation mark to indicate a send of a message on a channel. So this syntax indicates send message V on channel C, and then afterward continue with running process P. And then there's the important dual operation, which is receiving a message from a channel. This one takes a variable as an argument instead of a value. And what this means is basically block and wait until someone is trying to send a message to this channel, and then wake up and bind variable x to the message that you just received from that other party, and then continue running the remainder of this process, which now has variable x in scope to use to refer to whatever message came down the channel. And then just a few more constructs will be needed here. I'm going to introduce duplication, which effectively stands for infinitely many copies of the process P running in parallel. We'll see how to model that. And most importantly, we have parallel composition, which effectively says, here are two processes, run them at the same time, and let their atomic steps interleave with each other. And one more or less usual construct that just turns out to be a good one to give us a simple example to work with in Coq. I will give us a construct for hiding a channel, which is a barrier that prevents any sends into C from making it into the body P, and also prevents any sends that P tries to make on C from escaping out, so a receiver outside of this hide barrier could receive the message. So I'm going to model this in what's called a synchronous or rendezvous style, where the message sends and receives only ever execute when the send and receive on a particular channel are ready to run simultaneously, and then they rendezvous, and the sender passes off a message to the receiver, and they can both kind of unblock from their send or receive operations. And there's a classic style of giving operational semantics for these things called labeled transition systems that's going to give us a very nice way to reason about one process in isolation and then figure out what happens, for instance, when we compose it in parallel with another process without having to revisit the specification or the proof of the process that we compose. So to make that work, I'm going to define an operational semantics. And here's one of the most basic cases. when we have a process that wants to send a message, V, on channel C, this takes a step. And in general, I have these infix operator arrows for operational semantics small steps. And I'm going to put a label above each arrow that records what happened on this step. And if we want to run a send operation of send V to C, then the thing that happened on that step is that we sent V to C. So I'm sort of overloading the notation from the process syntax into the syntax of labels. So this notation says, I ran the send action, and what it did is it created a send, and then the code that's left over to run afterwards is just the body P of this send. So I'll just draw a horizontal line over that to mark it as an axiom of the operational semantics. And then we'll need the dual case. I have a receive operation. This rule is going to seem a little strange. At first it looks just like I switched some sends and receives around, but the interesting thing that happened here is this rule non-deterministically picks a message that's being received from somebody else out there. So there's this V, which unlike in that case where V appeared on the left-hand side of the arrow, in this case V does not appear on the left-hand side. It's being fabricated out of thin air, and we simultaneously drop it into the label associated with this step, and we also substitute it into the body of this receive command. And this is basically the key construction that makes it all work to give us nice modular reasoning about processes. And we'll need to look at the rest of the rules to see the rest of the plumbing that makes it fit together. But this is the really counterintuitive part. Semantics of a receive process is non-deterministically pick a message and just proceed as if that is the message you saw. And what makes this fit together as a semantics of the language is we can define rules like this one. There are actually two symmetrical rules. I'll just draw one of them here. If I have a process, P1, that manages to take a send step, sending V to C, and that steps to P1 prime, and I have a process P2 that steps to P2 prime, manages to take a step with the dual of that label. So P1 wants to send, P2 wants to receive. They want to send or receive on the same channel, and they've somehow agreed on which value is going to be exchanged. Then if I'm running P1 in parallel with P2, then this can take a step where both processes have advanced according to the assumption we have up here. And I'll just put an epsilon here as the label on this arrow to indicate a silent step, where we now consider this message exchange between P1 and P2 to be an internal operation, and we don't let the rest of the world know about it. This is an important kind of encapsulation as we build bigger message passing systems out of smaller ones. We want to not force everyone else who uses our library to know about all the details of all the message passing that went on inside of it. So in general, a label is either this empty epsilon marker, or it's a send, or it's a receive. Yeah?
The variable V missing at P2 prime?
Variable V missing for P2 prime. Which rule?
So because on both the upper and the lower one here, because it receives the variable over the communication, and the process after the receive basically needs the received message. Does it have to be shown that here?
You mean, for instance, in this premise?
No. In the lower one.
Here.
P2 prime. So from this notation, sorry.
Because it's already expressed, I think, in the axiom for receiving, it doesn't have to be expressed in the composition rule again, that in the typical case, the P2 prime is P2 with V for X.
Right. So this, nothing in this rule talks about taking the value that was received and binding it to a variable, because that's all encapsulated away inside of this rule. We don't actually need to mention it again down here. A few other key rules here. Again, this next one's one of a pair of symmetric rules, and I'll only show one of the two. If I have P1 and P2 composed in parallel, if I can take a step with some particular label, if the first of the two can take a step, and then we just port that change into the additional context that has a P2 sitting around there waiting to do something, and the label just propagates out to the top level. So with this rule, I could use this receive rule and then apply this rule a few times to add a bunch of other processes that don't get the step this time, and then use that to provide this premise. And then this sort of answers the question of why we don't have a substitution for a variable of the value v in this rule. It's because the actual receive action might be buried deep within the structure of P2, where we apply this congruence rule to let us get down into the structure at the point that's actually ready to receive. And it would be kind of complicated to talk about that substitution when P2 could have such a broad range of structures. Yeah?
You keep saying that you only show one rule of symmetric
Yes.
sets. It's to account with the commutativity and associativity of the parallel operator?
I think I could add a commutativity rule, and then that would remove the need to have the symmetric version of each of these.
Okay.
Of course, they're all in the Coq code, which we'll see shortly. I'm just giving some highlights on the board here. All right, so these four rules together are basically the big idea of the label transition system style to modular semantics. And I'll just give, let's say, two more rules to explain what duplication and hiding mean. And then I'll get to how do we state theorems about these processes and prove them. And okay, so what I want to say about a duplicate process, we can always step a duplicated process silently to spawn another copy of the body of the duplicate, and then the duplication itself sticks around. So notice this rule allows us to run forever, repeatedly spawning more and more processes. This just turns out to work well as a way of modeling certain constructions in this setting, and there are actually ways to implement these features, though it's not immediately obvious how to do that just reading off the operational semantics. Last thing I want to explain, the channel hiding construction. So we can take a step inside a channel hiding construction if I can step the body of the construction, get the same label that will be the final answer. Anyone have any guesses of an additional premise I'd put in here based on an intuition of what a channel hiding construction would do? Yeah, so one way to put this, let's say C does not appear in the label. So the label might be empty, or it might be a send or a receive. And I'm just writing this to say the label is not a send or a receive on the very channel that we're trying to hide here. So this is a nice modular way of expressing a barrier on messages going back and forth. Yes?
What can you do with channel C?
Internally, there could be several threads that use it to communicate. The communication happens only inside P, not with the outside world beyond this barrier. And this is really important to let us give succinct specifications of processes where we don't have to always worry, I meant this channel to be used for a particular protocol, and then there's some bozo out there who's sending garbage to it, and I have to be ready for that. Well, if there's a barrier like this, I don't have to be ready. The outside world can't touch my channel directly, and I have control over it. All right. And then the key thing, so this is just expressing what happens when you run a process. Now we need to be able to define a good notion for specifying a process, what we expect it to do, and we need to have good properties for composing these kind of results together. So the key definition that we use here is called refinement, and I'll be a little wishy-washy about defining it on the board because we'll go to the Coq code shortly, but I'll I'll just write it with a less than or equal to operator, which is basically saying the specification of P1 is P2. P2 expresses everything that P1 is allowed to do. And what does this turn out to mean? Well, we define it to mean there exists some relation R, which is going to be a binary relation between processes in the two sides of our refinement. And the basic idea is we'll be able to take any execution of P1 and then match it with an execution of P2, where at every step of this, this lockstep execution, the relation R relates the two sides. And I'll just use it.
At every step of the execution or after?
Every step. And I'll draw some diagrams that kind of illustrate this in an inductive style now. So assume I have P1 and P2, not necessarily the same ones up here, that are related by the R we chose. And now consider every step that we could take from P1 to some P1 prime that's generating a label L. Then there'd better always exist a step that P2 can take, generating the same label to state P2 prime, and then these new states are both still related by R. So in other words, every step P1 can take can be replicated by jumping to an equivalent P2, finding some step it can take, and then jumping back to a related P1 side process. And it's a little too restrictive for some of the examples I want to do to allow only this case. And I'll be a little wishy-washy here again about what these diagrams mean. But another case that should be okay is if I have related P1 and P2, and I'm worried about any step that P1 can take, but if it turns out to be a silent step that does not involve exchanging a message with the rest of the world, for instance, it's this step, or this one where a message was exchanged only internally, then this can give us P1 prime, and then this is okay as long as the new P1 state remains related to the old P2 state. In some sense, so P1 is an optimized implementation of P2, and P1 might take extra steps because of its clever optimization strategy that don't need to be reflected in P2. P2 doesn't actually do anything to model those steps. Yes?
You allow R empty?
A good point. It is important that the processes we started with are actually in the relation. Yes?
You said P2 is acting as the specification? Okay.
P2 is the specification of P1 in this notation. So if you haven't seen this kind of thing before, it might take a little bit to digest what all this notation means, but there's a really cool property that makes it all worthwhile to define things this way. I'll just try to fill in a theorem up here. Basically, R is a congruence for parallel composition, which means if P1 implements P1 prime and P2 implements P2 prime, then P1 composed with P2 implements P1 prime composed with P2 prime. So that means we can take a system that can be expressed as a parallel composition, and I can, in trying to prove that system, I can completely modularly decompose the goals into showing these relationships for the two sides of the parallel composition. So to hint towards some concrete hardware applications, imagine P1 is a processor and P2 is a memory system. And you have some clever ideas for how to optimize your processor. So you prove this fact, and then your friend has some clever ideas for how to optimize the memory system, and he goes and proves this fact. Then this theorem tells us, no matter what optimizations each of us thought of, then we have a black box way of composing together to show that the optimized processor and memory running together are always going to behave correctly. But we didn't need to do any